Okay, ma'am. Good afternoon, everyone. Welcome to our panel discussion on emerging technologies on energy storage devices, challenges, and prospects. I am Jushmita, a PhD scholar in the Electronics and Instrumentation Department at NIT Silchar. I also serve the role of webmaster for the IMS CSS SPS IEEE Student Branch Chapter NIT Silchar. So let's begin by introducing our esteemed panelists. First, we have Dr. Ganesh Madabattula, an assistant professor in the Department of Chemical Engineering and Technology at the Indian Institute of Technology, BHU, Varanasi. His battery technology lab at IIT BHU works on developing cell design and performance optimization tools for lithium-ion batteries and supercapacitors. He works on developing state of charge and state of health estimation and safety models for lithium-ion batteries. Before joining IIT BHU, he worked as a battery modeling specialist for Rimac Technology R&D UK Limited and British Volt UK. He obtained his ME and PhD from IISc Bangalore and carried out his postdoctoral research at Imperial College London. Next, we have Dr. Mayur Prakash Bonkile, an assistant professor at the School of Energy Science and Engineering at IIT Kharagpur, India. He works in the area of electrochemical energy storage and leads the Battery Engineering and Sustainable Technology Lab. His research activities focus on the engineering application of electrochemical devices such as batteries, with work including energy material, continuum level modeling, understanding degradation, thermal management system, and control. He was previously a postdoctoral research associate at the Dyson School of Design Engineering at Imperial College London, working on PyBAM Python battery mathematical model and open source battery simulation package under the Faraday Institution's multi-scale modeling project. He gained his PhD from IIT Bombay in 2022 on the integration of renewable hybrid power system with battery energy storage. And Mayur sir did his bachelor's in mechanical engineering in 2011 and master's in thermal sciences in 2015. And he's a science communicator and loves to explain scientific concepts to the public. And finally, we have Dr. Sanjeevikumar Padmanaban, a full professor at the University of Southeastern Norway and Murdoch University in Perth, Australia. Dr. Padmanaban's research focuses on advanced energy systems and battery technologies, particularly in modeling and performance analysis. He received his PhD degree in electrical engineering from the University of Bologna, Italy, 2012. S. Padmanaban has authored over 750 plus scientific papers and received the Best Paper cum Most Excellent Research Paper Awards and 5 Best Paper Awards from IEEE 16 Sponsored Lecture Notes in Electrical Engineering Springer Book. He is a fellow of the Institution of Engineers India, the Institution of Electronics and Telecommunication Engineers India, and the Institution of Engineering and Technology UK. He received a Lifetime Achievement Award from Marquis Who, USA, 2017 for contributing to power electronics and renewable energy research. He is listed among the world's top 2% scientists from 2019 by Stanford University, USA. He is an editor, associate editor, editorial board for referred journal, in particular the IEEE System Journal, IEEE Transaction on Industry Application, IEEE Access, IIT Power Electronics, IIT Electronics Letter, and Willy International Transaction on Electrical Energy Systems. Subject editorial board member, Energy Sources, Energy Journal, MDPI, and the subject editor for the IIT Renewable Power Generation, IIT Generation Transmission and Distribution, and Facet Journal, Canada. So today we will explore the current landscape of energy storage technologies, focusing on lithium-ion batteries, supercapacitors, and emerging innovations in this field. We will also discuss the challenges researchers face, including modeling difficulties, design constraints, and the important issue of battery degradation, which significantly impacts performance and longevity. I have Jayabrata Maiti with me, who is also a PhD scholar. Now I hand over the session to him. Over to you, Jayabrata. Thank you.
We can't hear you, Jaydatta.
Your microphone is off, I think.
Oh, okay. Am I audible now?
Yes, you are.
Thank you, Jusmita, for the introduction. Myself, Joyabruta Maiti, and I am the moderator for today's session. I welcome you all to today's panel discussion. We know that energy storage devices have become an integral part of our lives, powering everything from personal electronic devices to electric vehicles and even microgrid systems. With this increasing dependence, we encounter both exciting opportunities and complex challenges. Each panelist today brings a unique perspective and expertise on these subjects, and we look forward to learning from their insights and current state and the future direction in this important field. First, I would like to start with Dr. Madabattula sir. We know that there are different energy storage devices like lithium-ion battery, supercapacitor, and the lithium-ion capacitors also. So could you, sir, share your thoughts in brief of different energy storage devices, present status and future prospects, in your opinion?
Definitely. Thanks for asking, Jaydatta. So lithium-ion batteries are known for their higher energy density. They are the best among the devices that you mentioned, and a moderate power density. So they, because of their high energy density, they are considered for e-mobility. One of the reasons for that. And when it comes to supercapacitors have very high power density, and but very less energy density. So this restricted these supercapacitors to be used in electric vehicles, and then basically they cannot replace lithium-ion batteries because of this limitation, but they can complement the lithium-ion batteries in some ways, especially for peak shaving applications and as a backup for data management centers and data centers. So, and lithium hybrid capacitors, I worked a bit on them, and along with the advantages, it also comes with the combination of disadvantages of both lithium-ion batteries and supercapacitors. So that restricted them to be in major discussions among energy storage devices these days. So they come up with self-discharge issues and less energy density, less power density problems as well. So somebody has to work. Some people have to work on them. However, right now lithium-ion batteries and supercapacitors are covering the application needs of lithium-ion capacitors. So currently there is a limitation in terms of energy density. So though batteries are good, so they have a limitation in terms of energy density around 250 watt-hour per kg at cell level for lithium-ion batteries. This is best, but this is still causing range anxiety for these electric vehicles, and it's limiting applications of these batteries into transport, commercial vehicles, or eVTOL, let's say, vertical takeoff landing electric vehicles. So there is a range anxiety still available with the lithium-ion batteries. So the research is now focused on advanced batteries which can provide energy density beyond 400 watt-hour per kg. If we can come up with such energy density batteries, they can bring a lot of new application into our daily life, like ships, long-range electric vehicles, high commercial value goods vehicles, eVTOL, and all these things. So energy density is the one of the challenges currently the industry is focusing on, and as in India right now. cobalt is a critical mineral for making these lithium-ion batteries, and we do not have any cobalt in our country. So this is causing a geopolitical. Getting batteries also has some geopolitical issues involved in it. So industry now, India is focusing their research on cobalt-free batteries. It has to be both lithium-ion batteries, high energy.
Sorry, we lost the audio.
Dr. Madabattula, sir, your voice is not
Sorry,
coming.
sir.
Yeah. Okay.
Is it good? Did
Yeah,
you
it
hear
is.
so far what are
The last few lines
think-
but you are now audible.
So apart from, did you get was with me? Were you with me till a high energy density thing? If you can get a batteries beyond 400 watt hour per kg, that is good. And we also need cobalt free batteries in India. So we do not have that mineral in India that ensures energy security. So lithium sulfur solid state batteries or lithium manganese nickel oxide batteries. So LMNO, LMN, LMFP. So these are the current cathode materials industry is focusing on. And sodium ion batteries are another domain, which is mainly for energy storage, not for the e-mobility because of this limitation. Because sodium is still abundant compared to lithium, the industry wants to do that as well. Thank you.
Okay, thank you, Madabattula, sir. Now I would like to come to Dr. Bonkile, sir. Sir, can you please share your thoughts on the same?
Yeah, thank you very much. I guess it is a very excellent question to open this discussion. And Professor Ganesh has given a broad bird's eye view of all the present technology. I just want to share a small story because the question is the present status of all these electrochemical energy storage and future prospect or future challenges, what we would say. So this area, this electrochemical energy storage is highly multidisciplinary, at the same time interdisciplinary. So based on people's background, the present status and the future prospects, this answer may vary from their research domain. I will share my insights. Before that, a small story. So in a small remote village, once upon a time, there was an elephant first time in the history, and there was some blind persons in the village and they want to see the elephant. So the story, I cut the story short. So someone who touched the leg of the elephant says that the elephant is like a big pillar. Someone who touched the stomach say no, elephant is like a big wall, and so on. So battery is like that. So people from electrical domain are also working on battery. People from mechanical domain like me, they are also working back on battery. If you ask a chemical person or a material scientist, everyone will give you a whole range of answer of the present status and future challenges. Considering my background as a mechanical engineer, I'm master in thermal, I would say that, as Professor Ganesh very nicely explained, that lithium-ion battery is the predominant technology in all our consumer electronics, like our laptops and wearable gadgets like smartwatch and other stuff, electric vehicle, and now the renewable energy also. So this is possible because of their high energy density. And if you talk about the challenges, and the same is the opportunity for future, is the limitation in terms of charging speed. If you ask the electric vehicle owner, was one of the biggest bottleneck is the charging speed. Then comes the life cycle, where Professor Ganesh and I try to understand the degradation. And there is the safety aspect because of the thermal runaway issue, the fire incidents inside the battery. So all these are the present challenges in terms of lithium-ion battery, and same time provide the opportunity for the researchers to look into all these aspects. Future prospects, I would say, to improve the energy density, we should look more on the silicon anode. If not 100% silicon anode, some percentage of silicon in the present graphite structure, that can be a possibility. Then the safety aspect is because of the a non-aqueous electrolyte that we have in lithium-ion battery. Can we replace that with the solid-state electrolyte? That could be a strong future prospect for the lithium-ion battery research. So this will help us to increase the energy density and safety. One more aspect I would like to touch upon at the beginning of discussion itself is the recycling and sustainability of this lithium-ion batteries. Because now this EV revolution has started in India also, and we have our own net zero target by 2070. So a lot of electric vehicles are there on the road, but down the 20 years down the line, those batteries we have to recycle. So that's why we should develop our recycling ecosystem for all this battery chain, the entire chain from collecting those battery till the recycling. We have to look into that. Another aspect, like Professor Ganesh already mentioned about the sodium-ion battery, and CATL, one of the largest battery manufacturer, already started commercializing the sodium-ion battery that has a future prospect. Another thing about current landscape is now there are different players in this electrochemical energy storage domain. So techno-economic analysis of these different batteries is also an important aspect, because unless and until it is financially viable and profit-making technology, industry will not invest heavily into that. So if you want to go to TRL, technology readiness level 8 and 7, 8, 9, we have to make this technology commercially viable and attractive. And I guess regarding supercapacitor and lithium-ion capacitors, it's a domain of Professor Ganesh. He has very nicely explained that it combines both the advantages of batteries and supercapacitors. And for EV applications where we need a fast charging and moderate energy storage, this can be a good candidate. At the same time, in future, we should look at the hybridization of batteries as well as the supercapacitor, and how to make that a realistic proposal would also be a very interesting from a real life engineering application. So yeah, that's all my brief thoughts. Thank you.
Thank you, Dr. Bonkile sir. Thank you, Dr. Madabattula sir. Also, you have for your thoughts on this initial for beginning in the topic. As Dr. Madabattula sir mentioned, also Dr. Bonkile sir mentioned about the e-mobility and the net zero by 2050, that is we want to achieve. EV revolution has been started. So in this connection, I would like to come to Dr. Padmanaban sir. Lithium-ion batteries are the most popular electrochemical devices that we found, and EV is exponentially growing, as we know. So in this connection, we know that power electronic converter plays a very important role. So could you share your perspective on the role of power electronics on integrating this lithium-ion battery with electric vehicle?
First of all, I'd like to thank the organizers and Dr. Ganesh Madabattula and Dr. Mayur for sharing their experience and thoughts about the technologies in development of batteries. Yes, currently about electric vehicles is become a predominant solution either in a domestic application or a large scale application. The transformation become mandatory to overcome fossil fuels and to reduce CO2 emission by 2050. But already the Prime Minister of India, His Excellence, already informed that India will try to reach it by 2070 because of our population and infrastructure reconfiguration is required, and of course huge investment. In this case, my thoughts on electric vehicle is that currently I say 100% of electric vehicles purely depends on lithium-ion battery, as rightly mentioned by Dr. Ganesh and Dr. Mayur. In the future, we will have a big shortage because again, in my perspective, lithium-ion is again a fossil fuel, but it doesn't going to produce any CO2 emission because scarcity will come, and we can't able to again mine for lithium-ion. Currently, we depends on batteries from other countries, particularly India depends on China and other countries. Lithium is from Australia. In this case, the solution currently we have is to use lithium-ion batteries very effectively, and how we can try to use the energy density as well as power capabilities available in the batteries very efficiently and keep the lifespan. That's very important, because here I believe with the existing solution, it's going to exist for at least another 30 years or 25 years with the lithium ion batteries. There is no option currently. So power electronics converters can play a critical role, because everybody we discuss on developing lithium ion batteries, construction, electrodes, and how we can able to make more energy density as well as the power individual cell voltage developments, because lithium ion battery has its own classification, 5 to 6 types, and every type has its own lifespan. For example, I can say with my own article, I have published more about energy storage technology with the lithium ion. I can say life cycle, which is around 1500, with a temperature ranges from 0 to 45 power of 10 in case of lithium ion PO4. In case of lithium ion Mn, which is magnesium, which is around lifespan is 750. And the maximum lifespan for a lithium ion battery is a Li4 Ti5 O12 LTO, which is having 7000. And the bigger challenge among this classification of lithium ion battery is the cell voltages, which varies with a minimum of 1.2 to 3.3 volts. So even for an electric vehicle, we are configuring at 48 volt battery size of the battery is 48 volt, or 24 volt is required for the integration within the full electric vehicle. But electric vehicles are not purely DC. That is another challenge. So the battery has to manage the power capacity for DC as well as for AC. And all the cases, the battery is going to give only a low voltage. And the current requirement is very high, because we have an electric vehicle, say example, domestic application, we are loading. And there is a load within the vehicle by itself, as well as other loads includes the travelers and of course other commodities which are loaded in the electric vehicle. So the current requirement is very high when compared to the voltage. And for these reasons, a reconfiguration of motors which are driving the electric vehicle needed to be done. Then we have to have a protection units, luxuries requirements, which is AC, fans, audio systems, fancy lights. So the expectation of the consumer is beyond the limitations with lithium battery. So here how the technology comes, power electronics play a critical role, because batteries are only DC power supply with a low voltage, high current capacities. Here we need to enhance the power capacity for AC and DC. So power electronics converters like DC to DC and DC to AC plays a critical role in electric vehicles. And the most important that we are driving the electric vehicles not in a constant speed, depends on the road infrastructure, depends on the countries, and of course the elevations, because if you look at Norway, it's a mountain. If you look at also in India, Himalaya near to Srinagar, Kashmir is a mountain. And the driving requirement is not the same, powertrain requirement is not the same for the terrain or with respect to the hill stations are different. But the manufacturer cannot look that. They have to go with the same powertrain for the commercial business aspects. So here, the most important is the power electronics converter. We are talking about lithium batteries lifespan, reliabilities, etc. Who will take care? That's very important. When you apply a brake, you are going to generate regenerative energy from your motor, which will be pumped back to your batteries. It's not good. And if you look at the structure of complete EV, you have AC and DC, and the power quality. We talk about power qualities of these applications are very important, because they can generate reactive powers when an AC load is available. In a DC load, we will have a DC spikes and fluctuations. These all can affect your batteries. And all the battery manufacturers are giving only a lifespan for 8 years. The lifespan for your battery guarantee is only for 8 years, but depends on the road conditions, depends on the environmental factors, and frequent on and stop of your electric vehicles. Definitely the battery will not exist for 8 years. So the hurdle here is balanced particularly on the point of power electronics engineers, I'm saying, is the power electronics converters. So the modern technologies currently, we are using power electronics converters based on silicon-based versions, MOSFETs and IGBTs. But now the transition is going towards silicon carbide and gallium nitride, where these devices can able to withstand all these high propulsion of currents and voltages, and able to generate constant voltage and constant current, so that the most important feature is that the reliability of the battery can be ensured. And on these aspects, recently we had published a textbook, which is followed as one of the textbooks in Indian Institute of Technology in Varanasi, in the electrical department. We have done a complete theoretical analysis, practical approach, real-time implementation, along with my collaborator, good friend, Professor R.K. Sakat in the electrical department. And this textbooks, if you want, interested, you can have a look how we look the reliability of batteries, for electronics components, and how we can ensure the qualities. So all depends on two parameters: how we are making the devices integrated with the batteries and with the application part of your electric vehicles or microgrids. So here all are integrated, because how microgrid come into the picture, because we need a charging station, and the number of charging station is increasing. And when you have more number of charging station, the hurdle is for the grid, and the grid is not stable. How much it can able to be pumped when it is overloaded, then you create unwanted power. Again, it comes back to the battery. So there are many hurdles needed to be sorted out. And here the power electronics converters able to provide three different aspects with respect to the battery. One is to make the healthy condition. Who controls the healthy condition of the battery? We have the softwares. We monitor currents and voltages, even for each cells. Then we extract the parameters, and we want to maintain the voltage and current constant output from your battery. At the same time, if you want to charge, it's an additional process. So battery get discharged in time progress, then we have to charge. So the quality of waveform delivered, the voltage and current from the battery should be the same form it going to observe for charging. So all these parameters are absolutely controlled by power electronics converters. So power electronics converters, both the version DC to DC or AC to DC, can able to provide high current density, high power capabilities, and regulated power supplies with respect to the regulation of your electric vehicles or microgrids. But again, it's a big challenge, because batteries are given guarantees only for 8 years. For sure, by adapting with these electronics converters, we are trying to keep the batteries in a safe mode of operation, which includes a state of the charge. Say example, 80% you want to discharge, and 20% we keep the margin always with electronics converters. And the electronics converter ensures the quality of the waveform which the batteries can be charged. We have different standards with respect to IEEE and IEC standards, and of course European scale of standards we have. So these scales we develop electronics converters to ensure its lifespan can be used for 8 years. Again, it's a challenge always with the lithium-ion batteries to integrate, particularly for high power applications. Still now, there is no purely a lithium-ion battery-based high power train. We can't have a ferry. We can't have a ship, marine transportation, because marine transportation is the most pollutant when compared to road or to airways, where we can't put only batteries. So alternative technology is required. Here comes the critical play of power electronics converter, how efficiently we can integrate all these batteries with the renewables and transfer the power either through cables or of course without cables, because in the future the technology is going to be renovated by wireless power technology. And I can give an example in Indira Gandhi International Airport. In collaboration with me, I'm also working for that project with Dash Dynamics from Indian Institute of Technology. We are developing a large wireless power station, and the power electronics converters are already designed, where we use lithium-ion batteries. The guarantee is 8 years. But when the government is dealing with the project, they want to ensure how you are able to provide us the guarantee and reliability for 8 years. We trusted more more on electronics converters, minimizing the losses, power density, energy conversion, and efficiency from the available lithium batteries. But for sure, the people who are working more on lithium-ion batteries, like Professor Ganesh and Professor Mayur, knows the realistic problems. So here, it's not only the control and power electronics converter, but also the adoption of a modern AI technology is required. So power electronics converters play a critical role to enhance the capacity for the lifespan along with the control algorithms. But in the future, we are going to adapt more blockchain technology, machine learning algorithms, and cloud computing, because charging infrastructure going to increase like infinity throughout India, or if you consider Norway, any countries, it going to increases in a large scale. We are going to integrate more renewables, wind power, solar power, and all these batteries, lithium batteries, has to withstand a large power. Please consider, when comparing to wind power, we are going around 12 megawatt capacity. If you think about a battery, can you able to provide 12 megawatt capacity? See the size of the battery. And if you invest so much money on a battery, how you can get a reliability? So that's why the plans are slightly moved towards hybrid modules. We are working on hybrid energy storage technologies to use batteries like 40%. 60% is supercapacitors, because supercapacitors can store the energy as well as discharge the energy infinite time, and there is no degradation. For example, in batteries, stored energy can be discharged even if it is not connected to the load as a period of time, because it's characteristics. But supercapacitor is not like that, so there is no degradation. And for batteries, we need to charge only by using DCs. But for supercapacitors, we can use DC or AC. We can store the energy. And if you look at the pumping capacity, battery takes more time to reach the steady state value. Whereas if you look at supercapacitors, it's in fraction of second. It's very fast ramping action. That's why when we are looking at microgrids charging stations along with EV vehicles, we are working more on supercapacitors in combination with inbuilt batteries of electric vehicles. So supercapacitors along with batteries will be a prominent solution in future for electric vehicles, for domestic application, also for high power train. Because if you look at IC engine efficiency is much higher than an electric vehicle, because the powertrain is very high efficient based on fossil fuels, where that cannot be replaced only with batteries. So we need to look these microgrid technology along with the battery as a hybrid module. So not only supercapacitors, we are also working on fuel cell technologies, because fuel cell technologies can provide very high powertrain when compared to batteries or with respect to supercapacitors, and with minimum size. So size is very important. So all these three energy technologies needed to be integrated, and battery as a part of storage technology to use during the peak demands. Of course, supercapacitor is a storage technology. So with the combination of hybrid module will be the future focused along with AI, artificial intelligence systems to enhance the capacities. Thank you.
Thank you. Thank you, Padmanaban sir. So, thank you for your thoughts on this topic. Very interesting. As sir, Padmanaban sir mentioned about the battery lifespan and etc. It is very important that the health of the energy storage device. So it decays over time. So assessment of health of any energy storage device is very important. Dr. Madabattula sir, do you enlighten us about the present status on the SOH estimation of lithium-ion batteries, present state of art on the SOH
Sure.
estimation
Yeah.
on the lithium-ion
So,
batteries?
so my expectation is mostly based on physics-based modeling. It means I look at the electrochemical engineering principles within the battery, like Mayur, and develop models. So battery degradation is, we see a drop in capacity with time, but what are the reasons behind the drop? We look in those aspects like SCI, solid electrolyte interface reaction, that there will be a side reaction between lithium and the electrolyte in it, and lithium plating if we overcharge. There are mechanical fracture effects if we ramp it at high power. Uh, So these effects will be considered. These are the main reasons for loss of capacity. And I use these reaction mechanisms in our models to estimate, actually to predict. Estimation is easier. So you can do in the current day, let's say you can just discharge the battery at a certain C rate and measure what is the capacity has. So I would compare it with the previous initial value. But prediction is a challenge, and we do develop these models extensively, and they consider depth of discharge, C rate variation, temperature variation as per the geographical location, and storage SOC. So these effects will be considered in the model, and we predict state of health in the future and how long it can work. So maybe this is one approach we can follow. Mostly will be useful for improving the user experience. Yeah. So that's what in brief, about my work. Yeah.
Thank you, sir. One more thing in this connection, that is like for state of health estimation of the lithium-ion batteries, especially in case of electric vehicle, so laboratory-based experiments are not always possible. So in such cases, could you share your insights like on SOH estimation in real time without taking it to the laboratory? And how can we estimate the battery in real time, particularly in case of EV batteries?
So generally, we there is a research going on to estimate state of health based on partial charging and partial discharge curves. So this partial charging in a particular depth of discharge window or SOC window will give you the key features of estimating the state of health, and which will be very quick because we can't leave these vehicles for a longer time to test or estimate state of health. So there are mechanisms, and they use these partial charge discharge profiles, and
Dr. Ganesh, we are not able to hear you.
Yeah. Sir, we cannot hear you, sir.
Yeah, I think he has some issue with his hardware or Bluetooth connectivity.
So Jayabrat, you can wait for 30 seconds and then you can move to the other question to the other panelist. Yeah, I think you can move forward.
Okay, maybe Dr. Ganesh sir is having some connectivity issues. So we can come to Dr. Mayur sir. So while working on electrochemical energy storage devices, modeling is very important, as Dr. Ganesh sir was also talking. So can you give us some insights on the challenges that we generally face while modeling any electrochemical energy storage devices?
Okay. So yeah, as Ganesh was talking about predicting the state of health of battery, we have to model various battery behaviors, right? So first, let's split this question into two parts. Why we do modeling of any engineering system? One answer could be optimizing its performance and ensuring the safety, estimating its life, and how to improve its performance, understand its behavior in different operating scenario. That's fine. In terms of batteries, when we do experiments, right? So we can measure only three parameters: current, voltage, and temperature. So in this battery domain, modeling and simulation is very important to uncover the underpinning physical phenomenon that is happening inside a battery when you are charging or discharging. That we cannot experimentally observe. We can only see its end effect in terms of your voltage profile or current profile or how much power we are withdrawing. So that's why it's very important to model a battery to uncover the underpinning physical phenomena. And that itself gives you so many reasons and so many challenges that we face while modeling the battery or electrochemical energy storage, because this electrochemical behavior are quite complex because of their non-linear behavior and internal reaction. So we always have that redox couple, so reduction and oxidation. So this complex electrochemical dynamics that is happening inside a battery that involve ion transfer, mass transfer, charge balance, phase change, various changes in material level. So this complex this electrochemical dynamics and mathematically representing that in your programming is the first major challenges. And for that we required a deep understanding how this electrochemical system works, because even if you want to predict the state of health of a battery, first you have to understand from fundamental point of view why the capacity of battery degrades over the period of time. Once you understand that electrochemistry, then only you can model those behavior in your modeling and simulation tool. For example, lithium ion batteries, say LFP chemistry, is very sensitive to the phase change behavior in electron. Or if you have a silicon electrode or a graphite plus silicon, there is a hysteresis effect. Now it's very challenging how mathematically you will model this hysteresis effect in a silicon electrode. This is one part. Second is the multi-physics coupling. As the beginning of discussion, I mentioned that there are different research domain in battery itself, and all those are interconnected. This thermal effect, electrochemical effect, and electrical effect, mechanical stresses, all these physical phenomenon are interconnected. So when you are modeling the battery, you have to consider this multi-physics coupling. For example, if you increase the battery temperature, as Professor Sanjeevikumar was mentioning about if you drive the electric vehicle in the Himalayan region or in, say, in Rajasthan, right? So temperature difference is there. So this variation in temperature affects the electrochemical performance, and that leads to the mechanical stress. Now, if this is actually happening inside the battery, how you will model that? That's the another challenge. So this incorporating this multi-physics behavior is I guess another challenge. Next challenge is about the material that itself changes over the period of time because of aging, and which Professor Ganesh was mentioning. As the state of health was reducing, different battery parameters changes, and we know the materials are not perfect. We make a lot of assumptions while modeling. Okay, we make some like realistic assumptions, but some of the times we have to say, so for example, some of the electrochemical property are constant over the period of time that we have to assume. In reality, that might be the function of state of charge, or might be the function of temperature, right? So this how to model that creates another challenges for the battery modeler. Then, as I mentioned, we have to couple the different degradation phenomena. Coming up with a universal model is a key active research domain presently. What happened? People are modeling a particular kind of degradation or particular subsystem. If you want a universal model interconnecting all the different phenomena that I have mentioned, that will be a great help, and that will definitely improve the overall prediction and the software development in terms of battery domain. Next important thing, and there are a lot of research paper you can find, as a parameterization and validation. Because if you consider different kinds of battery model, and what Professor Ganesh is working on is the physics-based electrochemical model. And in any particular type of model that is very common, that's P2D or Newman-Differ model, or Newman model in general, there are almost some 39 parameters, right, that we have to estimate. So parameterization of different system, like different battery technologies based on the cathode, is a huge challenge for the battery modelers. And obtaining reliable experimental data is very crucial. So at the end of the day, experiments are the ground reality. We have to validate your model prediction based on the experimental data. Having the aging data accurately for real life is quite challenging. What Professor Sanjeevikumar was mentioning, if you can guarantee 8 years of life for a battery, we cannot run the experiment for 8 years, right? It's not, it doesn't make practical sense. So we have to obtain the reliable experimental data to get the parameters, right? So the model is like garbage in, garbage out. If you have an accurate parameter set for your model, your prediction will significantly improve. Next thing is computational complexity. So right now our mobile phones and laptops also predict the state of charge, whether it is 100% charge or 50% charge. So for that they use a simple models, right? But if we want to use more dynamics, predict the state of health and degradation, we have to improve the complexity of the model, and that is associated with the overall computational cost. So what I mean that you can simply program a microcontroller for a simple battery model. But if you want to use a physics-based battery model in your BMS, like a battery management system, it is not possible, because then the cost will significantly increase. Already the battery cost is a huge burden for any appliances. For example, if you consider electric vehicle, any OEM manufacturer, around 50% cost is for battery pack. And what Professor Sanjeevikumar is mentioning, if we are saying that 8 year is the battery life, right? So 8 years is a battery life. Yes, I can see someone raise the hand. No. Okay. So if 8 year is the battery life, after 8 year you have to change the battery pack. Okay. So which will add the cost to the already existing costly technology. And on top of that, if you want to use a very physics-based heavy electrochemical model in your battery management system, so it will again increase the cost. So that's another challenge for the battery modeler. And that's why we are coming up with a reduced order model, how to get the same kind of complexity, the real life prediction using a quite simpler model. Another challenge is between, I guess, academia and industry. In academia, we do the experiments in laboratories, so very highly controlled environment we have, and we develop our model, we validate our model in control lab experiment. But when you go to the real life world experience, right? So how the user will drive the electric vehicle, we have no control on that. Okay, so in this harsh real life parameters, I would say, or ambient condition, how those model or the electrochemical system will behave, we have very few information on that. So that's another challenge. And in battery domain, currently the industry is leading the research fund, so they have a lot of data, right? But right now in academia, we don't have that much data to train the model, and that's another limitation for the data-driven model, right? Because data-driven, like everyone is talking about machine learning, deep learning after ChatGPT and all those LLM models. So if you want to implement those advanced technologies, the data-driven models and algorithms, we require a large data set. And obtaining those extensive data set, high quality data for a range of temperature, range of C rate, range of different chemistry, and train your SOH model or aging model that changes from chemistry to chemistry, creates another challenge. And at the beginning, as I mentioned, from engineering perspective, that's a thermal runaway, like a fire in a battery. If you want to model that kind of behavior in your model, conducting those kind of experiments, and when your battery is actually on fire and getting the what is happening inside that, getting those data and modeling that, it's another bigger challenge. Again, is that when we understand any say electrochemical system, we go to the material level, what happens at material level for the diffusivity, rate of reaction, and when we transfer that knowledge to the cell level or battery pack or actual EV, so there is always a gap in between that. So how to bridge that gap is, I guess, another challenge that as a modeler we are facing. And I guess that's why this today's panel discussion is very important and at the right time, because we have people from different backgrounds are working presently, and there are also a lot of different challenges that we can address one at a time. Thank you for that.
Thank you, Dr. Bonkile, sir, for your thoughts on this topic. I think earlier we got somehow disconnected from Ganesh, sir. Sir, can you hear us now? Sir, we can't hear you.
I can hear
Okay,
you.
okay. Yeah, we can hear you. So as you were talking, sir, earlier about the ACI layer formation and other things. So several phenomena like LLI, LAM, loss of lithium inventory, loss of active material happens inside the battery while it is degrading. Sir, could you share insights on how these might be estimated using external measurements? Because from the battery, we can get only, as Mayur said also mentioned, the voltage, current, and temperature data that we can only measure. So because inside the battery, these things happens, LLI, LAM, ACI layer growth. So how can we estimate indirectly in these cases? If you can share us some thoughts on that. That would be helpful.
So definitely. So if we keep aside this physics-based, high computationally expensive data-driven models, so they need a lot of it, as just Dr. Mayur mentioned. So this is still a challenge. But if you want to measure this LLI LAM at faster rate quickly from the source information, there are a few techniques available in the literature people are currently using, like incremental capacity analysis and differential voltage analysis. These are the analysis that use voltage versus capacity profiles that we measured in real time. So they analyze the data and compare this voltage versus capacity of a cell with the cell which is fresh. So they compare the voltage versus capacity profiles of a cell and the new cell and come up with an analysis called this incremental capacity analysis or voltage differential voltage analysis to quantify what is lost due to LLI, loss of lithium and metal, which is responsible for SCI degradation, lithium plating, and how much has been lost due to LAM, loss of active material, in terms of mechanical fracture in the particles and some metal dissolution. So we can have some signs, signatures of these inside degradation mechanisms using these peaks in the incremental capacitance. So currently industry is using these techniques to analyze the state of health of the batteries.
Thank you, Ganesh sir. Now, I think I would like to come to Dr. Padmanaban sir. Sir, as your initial talks, you were talking about the fuel cell. Somewhere you mentioned. So, can you please enlighten us on what is the status of fuel cells, particularly in brief? What is the status of fuel cell based electric vehicles compared to lithium and battery based? So, if you can enlighten us on that, particularly on fuel cell based.
Thank you. I think Professor Ganesh and Professor Mayur has given a complete overview about battery technologies, particularly with the lithium ion, and what are the major challenges. Of course, these all challenges will come when a power electronics converter is connected with the battery. So these all challenges has to be overcome. That is the biggest role of power electronics engineers to ensure battery. Similarly, the fuel cell technology, why the fuel cell is coming? Because of the battery systems, which is having a low voltage profile, and the power rating requirement is required for a high power application is very deficit, because you need to have a very large battery banks to connect with large grids or high power trains, or of course for marine transportation or space transportations. I mean, for airspace transportation, it's not possible because the size is a big challenge. So in this case, fuel cell as one of the good competitor who can replace the fossil fuel and partly the batteries. So that's why I said from during my presentation, we are looking on hybrid renewable energy technologies, which includes batteries in a combination with supercapacitors plus the fuel cell technology. If you look at the fuel cell technology, the efficiency from the electrolyzer is only 60%. So we have to accept the fact. Currently, many research is going around in Europe, US, of course, in India with the CSIR laboratories. They are trying to increase these efficiency to 65% from CSIR lab in Uttarakhand. The Institute of Petroleum Institute CSIR, they are working to increase 5% increase in efficiency of the fuel cell. What is the advantage for going fuel cell technology? The power can be between less than 50 watts. The power can be less than 50 watts and maximum less than 100 megawatts. And if you look at the temperature adaptability, it can be suited for minus 20 degrees centigrade to greater than 800 degrees centigrade. So you can have an idea, even the cost of fuel cell manufacturing is expensive, but the adaptability for a different environment is having a huge space. And of course, the power capacity is very, very high when comparing to batteries. And and with respect to the supercapacitors. So now the electric vehicles are more focused on hybrid module, where fuel cell is a main powertrain and batteries or a subsidiary hybrid module to support, like in a percentage, as I said in the beginning, 60-40 percentage. So 60 percentage is from fuel cell we use for electric vehicles, and 40% as a margin for batteries. So the size of the battery can be reduced, and of course the lifespan is considered always. So fuel cell lifespan is much higher when compared to the batteries. So we are playing a critical role in managing all these renewables to be integrated into one platform. That's why fuel cell has a very prominent effects, either if you are looking at for a small vehicle or a large vehicle. For example, phosphoric acid fuel cell. Phosphoric acid fuel cell can be adapted between 1 kilowatt to 10 megawatt. And this can be used between a temperature of 80 degree to 300 degrees centigrade, and well suited for large electric vehicles, buses, train, tracks. But what is a big challenge? How to design the electrolyzers very efficient. As I said, 60% is the maximum efficiency we can able to get from the electrolyzers. And the cost of hydrogen is expensive, but the power density is very high. And by using electronics converters, what is a critical role? We can use these 60 percentage power very efficiently for the electric vehicles or integrating with the grids. So in Europe, already liquid to grid connection is already done, where hydrogen electrolyzers are integrated to the grid, and of course integrated to the electric vehicles as a part of the systems, where the efficiency is well monitored by electronics converters for its capacity by using silicon carbide technologies. But in the future, we are going to work more with SiC and GaN devices, where the reliability and energy transfer capacity of the electrolyzers can be done far better. But currently, the cost is the big challenge. That's why the industries like EV companies or microgrid developers are not much interested on silicon carbide and GaN devices. But in the future, the transition is going to happen, where the controllability, reliability, and energy transfer efficiency of these fuel cell technology will be much higher by integrating fuel cell and electronics converters. Also, as I said from the beginning, the control is very important, how your digital processes are working, integrating these fuel cells and electronics converters in a very short time, because we are not working on seconds, we are working in microseconds and nanoseconds. So we need a processes, the speed of the processors should be very, very high to tackle all these current regulations, voltage regulations, and of course for the protection. Dr. Mayur rightly pointed out, we are recently facing the big challenges with batteries burning, because battery flyover is happen because of the temperature and reverse flow of current. In electronics, we say these happen because of the reverse flow of current from the equipment towards the battery. And of course, the thermal energy will increase and you spoil the battery. The same will happen also for fuel cell. So all these cases, very large cooling systems, along with power electronics converters reliability. For example, the power electronics converter is working in nanoseconds and microseconds. The digital process should also work at that high speed, so that if there is any fault happen within the microgrids or electric vehicles, immediately the digital processor try to make the power electronics converter shut down, so that batteries, fuel cells, and all other parts of the electric vehicles are well protected. So here is the integration is the big challenge, and all the companies are facing. Currently, we are not using controlled devices for charging and discharging. We are using only uncontrolled devices by using diodes. But we create a lot of harmonics, and the reliability of the battery is coming down also for the fuel cell electrolyzers. But in the transition, we are going to use more silicon carbide devices and GaN devices, so that all these electrolyzers and batteries can be used for the defined lifespan and the quality. But on other side, as the people working on electrochemical aspects like Dr. Ganesh and Dr. Mayur can enhance the capacity of the battery individual cell voltages. So we are also working more with electronics converters, looking at each cell voltages by using IoT sensors. Also for electrolyzers, within the electrolyzers, how the technology can be improved to place IoT sensors, so that you don't need a cables to control the electrolyzers temperatures, and any flyover is happening during the hazardous conditions, so that we can able to break fuel cells or batteries from the main grid or microgrid, or from the applications of the various parts of electric vehicles. So these technologies are growing up, and in few years time, definitely the market we are going to see enhanced systems. Thank you.
Thank you, Dr. Padmanaban, sir. Now, someone when is working on this battery degradation, so I'd like to come to Ganesh sir. Sir, what is your suggestion, like, or can you suggest from your experience some software which will be best for analyzing the degradation of batteries or estimation of SOEs? What do you think, which software will be the best one, or some softwares?
So from the perspective of electrochemical engineering, electrochemistry, where we can enhance, where there is a possibility to enhance life of cycle batteries, I can share my views from that perspective, because these are the fundamentals will be used for cell design and improvement in cycle life and enhance the conditions. So for someone new to the field, I recommend COMSOL Multiplex as a software to jump in, so that it has extensive examples and features that one can understand the concepts of batteries modeling very quickly if it is a new. But it has some less flexibility. So if you wanted to do extensive research like Mayur did on silicon electrodes, so these such features are not always available in these commercial softwares. Then for advanced research, then we can use PyBAM, what Mayur and me have already worked on for advanced and features of making the batteries longer and understand the things better. So we can use PyBAM. PyBAM is an open source software. You can also jump into PyBAM quickly, but if you go from COMSOL to PyBAM, the experience will be better. Otherwise, you can still start from PyBAM. It's up to an individual choice. So these are my two recommendations for battery model regarding state of estimations.
Okay. Thank you, Dr. Madabattula, sir. Now, I think Dr. Bonkile said, as I came to know that from Ganesh sir's talk, that you have been involved in the development of PyBAM. So sometimes I have also seen to use the PyBAM. I have explored a bit. So it is a Python-based simulation package, and first of all, it's a very open source. So like as the Ganesh sir mentioned about the COMSOL, so compared to that, it is open source. So could you share us this tool, like how it might be benefit the researchers working on the battery SOH estimation? I think along with that, I want to add, like for one more questions, like as we work on the battery aging or battery SOH estimations, we need the battery aging data. That includes cycling aging test data as well as the diagnostic test data, like capacity test, HPPC test, that is hybrid powers, pulse power characterization, and electrochemical impedance spectroscopy. So can we generate this data by selecting any chemistry of the battery from PyBAM? So that is, if you can give us some thoughts on that.
Yeah, sure. Here I can see there are two questions. One is about general PyBAM, and then related to its capability. Right. So just let's address the first part. So as PyBAM mentioned, Python battery mathematical modeling, and as Professor Ganesh mentioned, it is open source. So let me share my own example. So when I was a PhD student at IIT Bombay, I start from scratch developing the physics-based battery model, the single particle model, and then P2D model. And after that, I did this degradation analysis and other part, correct? But now the battery field has evolved from 2014, 15, 16, that year. So why a researcher who is working on battery and some advanced aspect has to do all the basic remodel, the basic electrochemical modeling development? So the reinventing the wheel, why everyone have to do that? Because the most of the energy and time is consumed in that process. So that's one of the good aspect that this is available on GitHub. The basic model like single particle model and P2D model, all these different kinds of physics-based battery model, and even equivalent circuit model also are available in this open source model. In this machine learning and data-driven model, there are a lot of libraries, right? So those libraries, if you call and then you can use the functionality. So because of this kind of collaboration, that field has grown a lot. But in terms of a battery, it's very restricted to a particular research group. If anything is happening in that research group, stays in that research group except the paper. So most of the time, these codes are not available in the public domain. Most of them in paper, it is written available on the request. I don't know how many times you get a positive response from those. That's the one thing. Second, reproducibility of the scientific result, right? In battery community, if you publish some result, you should be able to reproduce that. In experiment, we can understand there might be variation in the temperature or the equipment or the accuracy of that. But in terms of modeling, if the code is available, you should be able to reproduce those results. So all the results that are available and the papers that publish under this project, which is funded by Faraday Institution, you can reproduce those kinds. So reproducibility of result is also achieved using such kind of code sharing. That is one thing. So there are a lot of inbuilt model available in PyBam, right? So most of you are from the electrical background and you may not be interested to learn all this basic electrochemistry and develop everything from the scratch. But for your particular research, you might be interested on state of health estimation and you want to improve your analysis by incorporating some of more physics into your research work. So for that purpose, you can download this open source tool, PyBam, which is available on the GitHub. They have very well maintained website also. And you can plug and play physics. That's they call plug and play physics. You can call different, if you have a basic understanding of a Python, and there are a lot of workbooks that are developed by the PhDs and postdocs who are associated with this work. You can start producing your own data, like state of health estimations and other things, from a simple 0-dimensional model to the 2-dimensional model. Then as we are talking so much about the SOH estimation, you can call different degradation mechanism like SEI-based solid electrolyte interface, or lithium plating, or mechanical stress if you have a particular kind of chemistry, for example, silicon, and that you are testing in your lab for some electrical analysis. So mechanical stress is a huge concern into that. And you want to validate some of your experimental data, or some electrical analysis needs some input from the electrochemical background. So for that purpose and for the aging study, you can do that. Then when, I guess, if you're working battery or supercapacitor, every device offers some resistors, right? So the resistance increase as the battery degrades. So that phenomenon also, and the capacity fade, you can model using the PyBam. And it has a very flexible module, like you can call some of the degradation, you can switch off the some other degradation. There are different basic libraries available you based on different cathode chemistries, right? Because battery is not only a black box, the NMC, LCA, LCO, different kinds of cathode, different kinds of anode. So that parameter set also you can call. So those libraries are available in the tool itself. Next is operating condition you can simulate. For example, as you are talking about the real life ambient condition, different temperature fluctuation, different C rate, different depth of discharge, different load profile. So that also you can simulate. So that flexibility is available. And another thing, it's like it's a free, it's a open source. For other commercial packages, you have to pay, or the institute or the government has to pay a huge license fee. And if you have some of those limitations, you can always go for these kinds of tool. It's quite efficient, easily accessible, it's fast. That what I can say, as compared to your own, if you just develop your own numerical models to solve the battery related equations, compared to that, is definitely very efficient and fast. And another important thing, you will get a community, as it is an open source platform. There is a very strong community on the GitHub or on the Slack who are helping each other to solve any issues related to this tool or software. And every year, like every year, 3 different versions, new versions, they add to this tool. And every time there are new features, new bug fixing, okay, new physics, new chemistry is getting added to this particular tool. So it is a pretty much evolving software, I would say. And if you are particularly from electrical background and quickly want to grasp some of the understanding of battery degradation and generate your own data for your research work, I think this is one of the best tools that we have presently. And the second sub question is about the different kinds of testing, right? So there is different kinds of sub modules in the PyBAM. So one of the feature is the experiment, right? So repeated charge discharge from a different state of charge or a different temperature. You can do that. Cycling aging testing also for different depth of discharge. You can generate your synthetic data for the capacity fade, increase in the resistance as the capacity decreases. So all these things are interconnected. So all kinds of tests, GITT, PITT, you can do, because what you have to do, you can track all these different electrochemical parameter once you pass the pulse, like current pulse, whatever this test. There are a number of different tests. So all can be replicated inside the that particular tool under the experimental class. So that test also is possible. The only thing is that as a modeling tool, it has some limitations. So if the model is validated for some operating scenario, and if you go extreme of that, so it may deviate from the real life scenario. So with that pinch of salt, you have to keep in the mind, and all experiments are the ground reality. But this is a very powerful tool, open source. And in February, like next year, February, there will be the first PyBAM conference. So that is happening at Imperial College London. Means in London, Imperial College London is one of the leading institution, but there are other UK universities also. And if you have done some of the work, as some of you might have done, and use PyBAM, so if the date is still open, you can submit an abstract or follow the website and follow the GitHub page and the LinkedIn community of the PyBAM, because frequently, like once in a 3 months, they release the new version to fix the bug. And every time, even you also, if you come up with some of the modification in the tool based on your background, mostly say electrical background, so that also can be a part of a larger public domain PyBAM. Or you always can have your own branch of PyBAM and start working on that. And I hope every one of you are on GitHub, or at least has a GitHub account, or a basic familiarity with the Git and GitHub desktop. This is very important nowadays, because this after this burst in the LLM models, there's a lot of development and new tools are available, and the same knowledge can be used in the battery domain also. So please go ahead and explore. And if you have any difficulties, or if you want some of the resources, you can always approach me, as I was just recently, like few months back, I was working on developing some of the sub modules. So I'm always happy to answer your queries, or at least guide to the most relevant persons, because there is a startup also out of the PyBAM. They are taking the industry problems and developing the sub modules for them based on the PyBAM. So yeah, it's a very exciting. I can continue speaking for hours together for this tool, because I have seen the development, but I think it's better to stop now. Thanks.
Okay, thank you, sir. We are actually moving towards the end of the session. So before going to the Q&A session, just in one word from the Dr. Padmanaban sir, what is your suggestion for the future researchers in this field?
Future research is having a wider scope because in 2050, many things will be batteries, fuel cells, solar, wind turbine, and photovoltaics. There is no other options we have. Where comes the important critical role is the energy storage technology, either batteries, supercapacitors, or the other means of innovations which going to happen in a few years. So there comes a critical role for, I say, electrical power engineers about voltage instabilities, voltage intrusions, sag and swell, and about how to manage all these batteries appropriately with large scale. For example, I can give you a statistics in 2030. If you are going to have EVs, it will be around 250 million tiny energy storage battery in the vehicle. So 250 million batteries will be running or standalone in some places across the globe. So there is a big demand for storage of energy. So all the vehicles in the future might be integrated with the grid, and every small batteries will become a renewable energy integrator or supply the power to the main grid. So there comes vehicle to grid technology. So each vehicle will part a power to the grid, and every vehicle can earn the money for its owner. The deal is already started, and I can give you a statistics in Europe, which is around 20% of demand response is focused towards vehicle to grid technology. But again, the big challenge, how to control all these batteries and renewables, which includes photovoltaics, wind turbines, and supercapacitors very efficiently, how to control to overcome voltage instability, current instability, reactive power compensation, and of course to maintain the power factor to get a maximum efficiencies. So all these challenges are one side for developing new control algorithms and new power electronics converters, new battery technologies and integrations. Another side has the renewables batteries, and we are talking about, yes, each vehicle, all these tiny 250 million batteries will be connecting with the grid across the world. Then who will monitor all these parameters? There comes artificial intelligence technologies. So there is a wider scope, integration of multidisciplinary activities in this field of energy technology, of storage or integrations. We need to integrate artificial intelligences and to ensure the robust operation, safety of the human beings. So all comes a critical play for energy management. So there is a scope for energy management. There is a scope for battery management algorithm developments with BESS. There is a scope for reliability testings, fault tolerant controls, and there is a scope for developing a new hybrid module. So we are talking a hybrid module either in parallel combinations, but we are not talking about a series combination. So in the future, series combination of connecting all these renewables may come with new technologies. So there are wider scopes for people who are going to work on batteries, fuel cells, and renewables. Thank you.
Thank you, sir. So I think we are at the end of the session. So we can go to the Q&A session. If the audience have any questions, please unmute yourself and I can ask the question.
So hello everyone.
Yes, you can go on. Suchandrima Datta, I think, raised a hand.
No,
You can
Steve Shankar
question.
is asking probably. So whoever is asking, please introduce yourself and start.
So I am Shankar Sinha, presently a second year PhD student in electrical department in IIT Gandhinagar. So I have two questions basically. One is from Mayur sir. So sir, you have spoken about thermal runaway. So could you tell us like few precursors from which we can detect and we can eliminate or suppress the occurrence of thermal runaway?
Okay. And the second question, like you want to answer me this
Sir,
first?
yes, yes, sir. That would be yes, sir.
Sure. So the fire incident in battery is known as thermal runaway. So the challenge is when we have a battery pack. Okay. So the question is how to monitor that and then suppress that, how to predict that if something is happening, something bad is happening in terms of temperature in the battery pack. So if we have consider a Tesla battery, Tesla electric vehicle. So do you know how many cylindrical cells they have in their battery pack? So in terms of thousands. So the answer is roughly they have 7,000 plus minus cells. So because of any reason, say whether it might be a material problem or say manufacturing defect or some issue related to the battery management system, one cell is overcharge or over discharge or some internal short circuit because of the lithium plating degradation happened, there is a sudden rise in the battery temperature. Okay, so the battery management is designed either to monitor, as I say, current voltage temperature of the particular single cell or a group of cell or a battery pack. So the most important thing is that it's very difficult to predict it in advance. We can just switch off that particular cell if we recorded abnormal voltage behavior or abnormal current behavior comparing to the other battery cells on that, because this redox reaction, the generation of heat, is very rapidly happening once there are different stages of the thermal runaway. So from like rapid increase in stage, the melting of separator and consumption of current collector and so on that we can explain in detail. But one of the signature that we are talking initially about state of health also, same can be applicable to for the thermal runaway. How to control that? It's very difficult because once something has started uncontrolled reaction, it's very difficult to stop that at particular stage. We can just see if it is stationary storage, we can just remove it from the main battery energy storage system. It's in an electric vehicle. Only when the smoke start coming, we can see the visual eye. And I guess Professor Sanjeevikumar can be an expert in terms of power electronics, how to predict that in the advance. Any thoughts on that, Professor? I would like.
Yes, as I said, in the modern electronics, the only option is to withdraw the batteries. So we have a energy management system, best battery management systems, where we predict the current and the voltage, and we keep the threshold. So we don't look at individual cell as a source, because it's a bulk source for 48 volt. When the current capacity is either exceeds the threshold or the thermal runaway is happening, thermal temperature is running above, we try to eliminate the battery from the connected loads. The only option we have. Other option about the cooling system. So immediately the system has the algorithms try to either use a fluid dynamics to make no firing happen within the battery. So by using cooling systems and production unit, we try two ways, pumping more fluids and make firing not to be happen. Another possibility is within the pack, the battery will blast, but external equipments will not be spoiled. But if the battery management system fails, then it is out of control.
Yeah, and around 140 degrees Celsius, the separators start melting, and then other things happen. So you should not use that particular battery or that cell after that, even if no sign of smoke or the fire. Internally, everything might have collapsed.
Yes, and I think the modern vehicles doesn't have. In research, we are talking on individual cell monitorings, but in real vehicle, the companies cannot afford, because each cell they can't monitor the voltage and current and temperature. So it's a pack. array. They usually they try to, for example, BYQ is doing or Tesla is doing for a pack is done. For array of battery cells they are doing, but not for individual done. It's very expensive. So the most easy is the thermal limits and the current barrier we control, and we eliminate the battery from the connected loads in the electric vehicles or microgrid, and try to pump the fluids to minimize the adverse effects. This is the possibility. But if there is, as I said, there is a problem within the integrated systems, it's beyond the control. That's why many firing happens across the globe, where the battery. Also, there is some possibilities. We have some guidelines for the designing the batteries within the electric vehicles, but sometimes the companies, based on motivation towards business model, they are overcoming all these regulations. This is also one of the reasons we are getting these problems. Also, another practical problems like developing countries, we have a guideline. This is the maximum load you have to put it in an electric vehicle with the batteries, but they are not following. They put 3 times, 4 times the load, and all these damages also came because of the human errors. And this needed to be trained for the those who are non-technical people, or the consumers must be trained for these regulations. That's very important, I feel.
So yeah. So this is one of the reasons. On a lighter note, as a joke, I just sent a news article in the chat. I hope you can see that. So there was a dog in the house, and they was chewing the power bank as no one was there, and that caused the huge fire for the house. So this kind of situation are out of control. If dog is chewing the power bank, the thermal runaway will happen. So we call it as a mechanical abuse. So such kind of things also happen for thermal runaway.
Yeah, thank you so much, sir. But like, sir, not every thermal runaway can cause or lead to fire. So I wanted to ask, like, what are the different precursors which can, like, we can detect that and we can say, okay, now this thermal runaway can lead to fire or explosion. So are there any gas detection or any voltage detection? So that perspective I wanted to know, sir.
From me?
Yes, sir. Yes, sir.
Yeah. So as Professor Sanjeevikumar mentioned, we monitor the temperature, right? If the temperature is crossing this 70, 80 degrees Celsius, then it may lead to the thermal runaway, because after 100, everything become out of control and different stages. And when it's crossed 140 degrees Celsius, the separator will melt, and there will be a short circuit, and again spike in the temperature. So the simple answer could be monitoring the temperature. It should be like, if it approaching 70, 80 after cooling also, that you are circulating the coolant, then there's seriously something wrong inside the cell.
Thank you so much. Thank you so much.
Thank you.
We can see that Varuna Roy and Sushandrima Dutta have raised hands. So if you have any questions, please unmute yourself and ask your question.
Yes, I can go next.
Yes, you can.
Yes. So good evening, everyone. My name is Sushandrima Dutta, and I'm currently pursuing MBA in Energy Management from IISWPM. So my first question is, like, firstly, we have heard we have to put more focus on recycling of lithium ion for continuing the use of EV vehicles. So, according to from the energy manager's perspective, can we use the solar energy instead of lithium ion for the use of the EV vehicles? And also for the hilly areas, what are the concerns that we should keep in mind so that there also we can use the EV vehicles? And my second question is, for the future aspect, we have the AI and the hybrid models and also the supercapacitor. So what is the role that needs to be played by the energy managers respect to that?
Okay. Mayur sir, can you please?
Okay, I guess the range of question covers the entire panel discussion. That's good. So I'm slightly confused with the first part of question, the comparison with solar energy and the batteries. So is it correct, or like I understood it wrongly? Can
No,
you just
the
clarify the
solar,
first part?
yes, the solar energy, like any renewable energy can replace the lithium ion, like for the longevity of the EV vehicles to run in the future.
I think she's talking about integration. That means hybridization with the renewable.
Yes,
So
yes,
that
yes,
lesser time you have to use the storage battery.
storage batteries.
Okay, but in terms of electric vehicles, if it is a battery electric vehicle, we have batteries, and for the charging purpose, we can use renewable energy. So that makes sense. But
Or are you thinking the rooftop kind of on top of the
Yes,
vehicle
yes,
you want to put? I think she's talking about
okay,
yes.
solar-based rickshaw and all.
Yes.
okay,
Because in
apply
the
the solar
taxis
panel
we see the
on the top
plants
of.
are there, the rooftop mechanism. In different cabs we generally see nowadays, like there is some cooling system with the plants on the top of the taxis or the cabs that we travel. So like that, any mechanism can be implemented for the EV vehicles with respect to the renewable energy.
I don't have answer for that. I don't know, but if you have a solar PV panel on top of a vehicle, it will have all the disadvantages that we have in general as a solar as a renewable energy. So that's why,
I
and
just
one is energy
Dr.
generation
Ganesh
and
wants to
batteries.
say something. Sorry to interrupt. I think
Yeah,
Dr. Ganesh, would you like to address it?
Yeah, actually, solar panels are energy generators. They are not meant for storage. For example, it is okay to have a solar panel on a car, but the car can run only when there is a solar or sun available, and that energy can be used. So the power, the speed of vehicle will directly dependent on whatever the energy being generated by solar panel. So when there is no light, solar panel can't provide energy and car cannot move. But lithium-ion batteries are storage, so they cannot generate energy. They are just meant for storage. So whether it comes from renewable energy, solar panels, or grid coal, they can store energy, can be used whenever we want. So this is the major difference between having solar panels on EVs and batteries. You cannot get away with without lithium-ion batteries. So we need storage. That's the main thing.
I think Arunav Roy has raised question. Arunav, if you have any question, kindly briefly go through.
Yes, sir. I'm Arunav Roy. I'm a research scholar at NIT Silchar AI department. So my question is basically to Ganesh sir. Sir, I am working on lithium-ion capacitors. So I would like to know what are some of the recent trends of research in lithium-ion capacitors from a chemical engineering point of view.
So I worked on this lithium titanium oxide as one of the electrodes in the activated carbon as the one. And these days, people are, instead of combining lithium as one electrode and activated carbon as another electrode, people are coming up with pseudo capacitors. There are also hybrid capacitors. So you can mix double layer contribution and electrochemical contribution in one electrode as a cathode, and in the same we can do it in the anode as well. So that is still an active area of research. I cannot conclude clearly say that this is the one that someone has to focus. So there are several possibilities for this particular lithium-ion capacitor. Sorry, I do not have a clear answer for your question.
Okay, sir.
Thank you, sir. Any other questions from the audience? We are moving towards the end.
I think you can take Khader's question at last, maybe. Yes.
Suporna Maiti and Khadir to our left.
Sorry to interrupt. Please note, you are not clearly audible, Suparna Maiti.
Okay, then maybe that's why I'm not again.
So I think there is some connection issue from the side of Suparna Maiti. You can put the question in chat box, we can ask. Any other questions from the audience?
This you can conclude better.
Okay. So now I think Jusmita.
I have a question.
Okay, please go ahead.
Okay, Sanjeevi sir, as you said that in the coming decades, million of batteries will be connected to the grids and AI can be useful for that. So I would like to know what artificial intelligence methods or the technologies can we work on for grid connected batteries, and what kind of problems can be anticipated? These are the two questions.
The anticipated is a very good question. So because when 250 million small batteries going to travel around the world as a storage energy, who will monitor all these batteries? Who can monitor so much data? So there are a lot of data needed to be processed. So we need to create a blockchain, and all these data need to be stored in cloud computing. Then we use machine learning algorithms to train these models to behave the model as a real scenario. So these artificial intelligence algorithms will come into pictures to control all these batteries within the vehicle as well as externally from the headquarter centers. So in this case, the most important challenge is, as you know, the reliability of batteries are limited and they are very sensitive. For example, if one battery got a faulty action from one vehicle, that can generate a lot of unwanted component. I'm talking in general because I don't know about the expertise of the participants. So it can create a lot of voltages and current, which can affect the neighboring batteries also. So there is a challenge to maintain the reverse flow of current from the neighboring batteries or from the grid, where we need a total protection. And the batteries, when they are connecting with the grid, they can parallelly also connect it to other applications because we are working for V2X. So X can be any load, it can be a home, it can be a local centers, etc. So in this case, your small batteries of 48 volt with a capacity say around 10 kilowatt hour capacity, then this is a very strange phenomena where always this battery is connected to a high power system. So protection is a big challenge. Communication in a short span is very big challenge, and how to effectively optimize and prevent any hazardous action created in the batteries. For example, thermal runaway can happen in a fraction of a second when a reverse flow of current is coming to the battery. So all these cases, these predictions can be done in a short span only by using, if the data is available in the cloud, in a nanoseconds or microseconds, and by using machine learning algorithms, which is much faster than other predicted algorithms to take action which is already predefined. So that's why I said it's an integrated systems. That's why we are working more on cyber physical based power electronics applications. So there is no gaps to fill. These technologies work separately, so it's all integrated.
Thank you, sir.
Thank you, sir. Thank you for the thoughtful questions and interesting Q&A session. Now I hand over the session to Jusmita to conclude.
Thank you, Jayabit. Thank you, Dr. Padmanaban, Dr. Madabattula, and Dr. Bonkile for your valuable insights. It was a wonderful and very informative panel discussion. We hope this discussion has enriched our understanding of the challenges and prospects in energy storage technology. And also, I would like to thank to the audiences for your engaging questions and for joining us today. And one more question we are having for the respected panel members. So if anyone wants to collaborate for the future upcoming years. So can we provide your contacts to the participants or the person who wants to work with you?
They will get it from their websites only.
No, we are taking their consents. Then can we share? Okay. Okay, thank you so much, everyone.
So I think before really we can have a photograph of this session together. So if everyone can please turn on their cameras so that we can take a screenshot of this event. So it'll be nice.
And happy Diwali to everyone.
Happy Diwali to all.
Yeah, the session has been really great.
Yes, thank you very much for everyone. So please turn on your cameras once so that we can have a photo. So we'll just take a snapshot of this screen.
Mayur might be missing.
Yeah, in the front page he is not there.
I'm not there. Sorry.
Yes,
Do I have to speak?
No. In my screen, you get. In my screen, everyone is visible. So I hope
that's good.
Things are fine.
Please share the photo after that.
Yeah, sure, sir. Okay, sir. Just wait a moment. I'll just let you know when it's done. Okay.
You done?
No, wait a minute. Yeah, thank you. It's
Thank you
done.
so much. Thank you, Dr. Ganesh. Thank you, Dr. Mayur and Dr. Padmanaban. Thank you so much for your time. And sorry to call you on the pre-Diwali time only. I really feel sorry, but it was a great success. Thank you so much.
Thank you.
Thank
Thank you very much.
All the participants, thank you so
Thank you.
much. Happy Diwali.
Happy Diwali, guys. Thank you.
Happy Diwali,
Bye.
everyone.
Happy Diwali.
Bye.
Bye bye.
Good.
Happy Diwali to everyone.
Bye.